maintain the number of times we have pulled the arm. We denote it by IT. IT means that we have pulled an I up to T this number of times. Oh no, sorry, I'm stupid. NIT, okay? NIT is number of arms we pull until T. IT is the arm we're going to pull at time T. So we're going to maintain the average, estimated average of the reward of each arm I. And this is, it looks like a complicated actually. This is indicating the function. This is the number of rewards we achieved so far, and divided by the number of times we have pulled the arm so far. Okay? Very simple. So this is the average reward of that arm up to time step T. Once we have these things, we define the UCB index as follows. We take the estimated average, we take the average, and we add to it this arbitron, which is 2 log T. T is the number of times so far, divided by the number of times we have pulled the arm so far. You take the square root of it, and you multiply with C, which is the bounded support. Okay, that's the index. And then the argument, what it does is that it says that each round, you calculate the UCB index of each of the arm, and then it chooses the one with the highest index and to pull that arm. Okay? Once it pulls that arm, it observes what it got, updates the index of that arm, and the next round it will pull the one with the highest index again. Okay? It doesn't have to be the same as previous round, it can be another one, but every round it just maintains its indexes, and then it always chooses the one with the highest index. That's all. That's all about UCB. Right? Any questions about this? You want to do some examples, calculations?
We update policy after doing some so how many times does we need when doing this to look?
That's one. I mean, the number of rounds we have is given. Like we have to play the game for 1,000 rounds. Yeah. So every round, you choose an arm with highest index. You pull the arm, you see the reward, you update. Yeah, because what you need to update is that you need to update to increase this value because we have pulled it one more, right? One more round. This will be increased by 1. This might change. This value might change because it can go up, go down. It depends on the reward you get, right? And this value also changes by 1 because it's the next round. Okay? So every time you have to update the indexes for all the arms, and then you choose the one with the highest new index. Okay? So each time we pull only one arm. Any questions about this? Not then. But I will spend the last few minutes of the first slot to prove why this is good. Yeah. So this is an expected value. So this is just a general definition, right? So x is a random variable. Okay. Mu is expectation, it's expected value of that random variable. This is the empirical average, okay, the empirical mean. You sample several times, you sample from the distribution x, you take the average, and you denote it by x hat. And index here, with the subscript here, denotes the number of samples of that distribution, random variable. So then, we want to do something called Hemping's inequality. Have you heard about it before? Hemping? Well, Hemping Azuma, Hemping channel. Okay. So it says that it's a very nice theorem. I encourage you to use this one. So it says that whatever you do with the average, with the empirical mean, the distance between the empirical mean and the true mean cannot be very large. Okay? So this is your high level explanation. But more formally say that the probability that the empirical mean is larger than the true mean by epsilon, that probability is going to be exponentially smaller. How exponentially? So we say this is E, the logarithmic base, and the exponent here is -2 times n the number of samples, multiplied by epsilon squared. So the more samples you have, this becomes smaller. It means that it's a kind of a finite time. You could say it's a finite time version of the stability theorem, for example. Right? So the more samples you have, the average, which is the empirical mean, is going to become closer and closer and closer to the mean, to the true mean. Okay? It's opposite also true. It cannot be much smaller either. Okay? So this is a symmetric statement. And that's a very nice theorem. Because if we use this theorem, then what we can do is that if you look at the index again, so this is the UCB index of an arm, then by using Quirking, you can actually prove that the probability that our index is going to be a little bit smaller or smaller than the true mean, that probability is going to be exponentially small over time. Well, sorry, it's not exponential, it's very small, not exponentially. Doing the proof, you will see how much small it is. Okay? So it's unlikely. And that's a very nice thing. And because of this, it means that this index is always, or almost most of the times, is kind of like a very good estimate of this one, of the true mean value, but it's always higher. Okay? So that's why this type of technique is called learning or optimization in the face of optimism. Optimism means that we always believe that we always have some kind of like overshoot. Okay? So, are you ready for some math in the morning? Yeah. Okay, very good. So let's do the math together. But before that, I would like to mention something. So why is this good? I mean, the whole philosophy behind UCB is that why we want to put the algorithm high-S index. And the reason is because when you ask the question in the reverse way, when it has a high index. And the answer to this question, it has high index because either this value is already high. Right? It means that because of this, it means that this is already a very good estimate of our arm. So it's likely there's going to be a good arm. It's likely it's going to be optimal. Or in other situation, it is high because this is very high. And this is very high means that there are lots of uncertainty there. So we know anything, we don't know anything. So we want to explore more. So the very nice combination of exploration and exploitation within one single step. Okay?